Section 4.4, exponential and logarithmic equations. The goal here is to be able to solve exponential equations, and there are two methods that we can use to solve exponential equations, using like bases and using a property called one-to-one property. And we also wish to solve logarithmic equations, equations that contain logarithms. And we can do that by using the definition and converting to exponential form, or we can use a different one-to-one property to solve these logarithmic equations. And we can also look at an application problem involving exponential and logarithmic equations. Let's take a look at what it means, use like bases to solve exponential equations. Expressing each side of the equation as a power of the same base, if possible. It's not always possible to do that, but if you can, and you have the same number on both sides as the base, then the exponents have to be the same. Otherwise, you would say something like 2 to the third power is the same as 2 to the 10th power. You know, if 2 to the third power, very quickly here, if 2 to the third power equals 2 to the x power, x must be 3, right? Because then you'd have equality. 2 to the third equals 2 to the third. There's no other way that we could have equality without x being 3. So it seems to be a statement of the obvious, and it is, but it actually provides insight into how to solve more complicated problems. So we'll first get the exponential equation written in this form if we can. Then we make an equation out of the exponents, and then we solve for the variable. Okay, let's see this in practice. So here is an example. Solve 5 to the power 3x minus 6 equals 125. Notice the bases here are not the same, but 125 can be expressed as 5 to the third power. So now we have the base the same, therefore make an equation out of the exponents and simply solve for x. And you get the solution set there being just 3. Okay? We have another example over here where we have 8 to the power x plus 2 equals 4 to the power x minus 3. Now, 8 is not 4 to a power, and 4 is not 8 to a power. So it's not so easy as this one over here. But 8 can be written with a base of 2. In other words, 2 raised to the third power is the same thing as 8. So this is identical to what we have written here, except we write 2 to the third power instead of 8. 4 is 2 squared. So this reads exactly the same as what we have right here. Now, before you move forward, use a rule of exponents. A power raised to a power multiplies. Power raised to power multiplies. Okay, now you have a big example of b to the m equals b to the n. So make m equal to n. Make an equation out of the exponents, and easy to solve for x, and you get the solution set being negative 12. Okay. So that one you might have to verify on the calculator that x equals negative 12 is actually true. Okay. Using logarithms to solve exponential equations. Okay, if you have an equation that contains an exponent, and in the exponent you have a variable, and you want to isolate that variable and solve for it. The problem is, see, like right down here, the exponent is up there, and there's no way to get it on the ground to solve for x. But there is a way, and that's what this is describing. Isolate the term that contains the exponential. Take the common log of both sides of the equation. Well, if you have base 10, you can do that, and otherwise you can take the natural log if you have any other base than 10. And then simplify using the inverse properties, or you could say the power property. It's one and the same. And then you can solve for the variable. So let's see how this works. 5 to the power x equals 134. Now, 134 is not 5 to a power, so we cannot do this the way we did in example 1. So what we'll do is we'll take the logarithm of both sides. Here we're choosing natural log, and we're doing that because we don't have numbers that are powers of 10. So common log isn't very useful there. You could still take the common log. That'll still work. There's no problem with that. Or you can use a natural log. So by taking the log of both sides, now use the power property. The x comes down in front as your multiplier. See, now it's on the ground and you can get to it. This is just a number that multiplies x. So we can then divide both sides by the log of 5 and end up with our result. But there's no reason here why you can't, say, do the following. 5 to the x equals 134. We could take the log of both sides, the common log of both sides. A logarithm is a logarithm. It's only a matter of how it looks, and how it looks is what base you choose. This would be x times the log of 5, and that's the log of 134, and then divide both sides again. So it's the exact same algebraic steps as right over here, except now we have common log. Now think for a second. We used the change of base property before. You can convert from one base to another. So really the difference between these two is just a conversion of base. Try this on the calculator and you will get the same result, in fact accurate to all decimal places. So whichever logarithm you wish to choose, meaning the type of base you wish to choose, is perfectly fine. Let's see another example in action, something a little more challenging. Here, example 3. Solve 3 to the power equals 7 to the power. Now, see, 3 is not 7 to a power, and 7 is not 3 to a power. So once again, we can't use like bases. So what we're going to have to do is take logarithms. So the choice here has been made. Take the natural log of both sides. Now we have log of m to the p, log of m to the p. So the power property applies. Notice the use of the parentheses here is mandatory. If you don't use the parentheses, you have the wrong result. Because then you have to distribute this to each quantity. Why? Because x is in here, trapped by the parentheses. The only way to free it up is to multiply. Natural log of 3 times 2x minus the natural log of 3 times 1. And do the same thing over here. Now this has your variable in it. Over here has your variable in it. Let's get them on the same side. This term does not have an x, so move it to the other side. And then, let's see, how do we then solve for x? Well, we have two terms that each contain an x, so factor it out. This then becomes the big multiplier on x. So divide this side and this side by that multiplier, and you will then have your result. I encourage you to try getting this on the calculator, and if you do that, I would put parentheses here in the numerator, and I would put parentheses here in the denominator. Otherwise, you will not get that result. You'll get something different. Go ahead and try it. Using the definition of a logarithm to solve logarithmic equations. So these are equations that contain a logarithm. Okay. There's two ways to go about this. Express the equation as a single logarithm, and if you can get it that far, then you can use the definition of the logarithm to simply rewrite it, that the base to the power equals the number. So this will take it from a log equation into an exponential equation. Okay. Then we have to check our proposed solutions to see if they violate any domain issues. In other words, the logarithm is only defined for positive numbers, so we have to always check to make sure that that is true. So here's an example of this very idea. right here, example number 4. So we've got the log base 2 of x minus 4 is equal to 3. So this is a log equation because it contains a logarithm. And we need to get out of the logarithm. So we will get it to, by the definition, transform it to be an exponential equation. The base to the power equals the number. And that's what we got right here. That's what happened. We changed from log form to exponential form by the definition. Now 2 cubes 8. Add 4 to both sides. X is 12. Okay. Always check solutions to logarithmic equations. Okay, so we say x is 12. 12 minus 4. Okay, that's 8. That's positive. That's good. In other words, it doesn't violate any domain issues there. Not only that, log base 2 of 8 is exactly 3, and 3 is exactly the result we're supposed to have. So we know for certain that this is the solution set. Okay. Here's another property, different method of how to solve logarithmic equations. Express the equation as the equality of 2 logarithms. Okay. Important that the coefficient, the multiplier, is 1 on each side of the equation. That's very important. If it's not, you have to use the power property and put it up there as the power. You also need the basis to be exactly the same. Okay. Use the one-to-one property. So in other words, if log of A equals log of B, A must be equal to B. That's the only way, as long as the bases are the same, to make that equation true. Then we can solve for the variable and we can check our proposed solution. Now we don't have an example of that on the PowerPoint slide, so let me push this up here a little bit and I'll try to squeeze right in here an example of this very property right here. So let's say the equation is common log of 2 is equal to the common log of x squared minus 7. Okay, we have the same base on both sides, base 10. We have log m equal log n. Therefore, m equals n. That is the one-to-one property. So, okay, that's what they're talking about right here. Let's use that, and then you'll see solving for the variable is fairly easy. So this then is 2 is equal to x squared minus 7. There's m equal to n. You can add 7 to both sides, so 9 is equal to x squared. Therefore, x is equal to plus and minus 3. And check the answer. Positive 3 squared is 9. 9 minus 7 is 2, so log 2 equals log 2. And negative 3, of course, squared is also 9, so we end up with the same result. So the solution set is both negative 3 and 3. You have to distinguish between a number that's negative in the answer is fine. It's that we can't put that number back into the original and end up with the logarithm of a negative number. That's the problem. And sometimes you throw out negative numbers, and sometimes you throw out positive numbers. It's that you have to check the domain in the original problem to make sure, back up here at this stage, to make sure that your answers satisfy the domain issue of logarithm of a positive number. Okay, let's take a look at an application example here, example 5. How much time to the nearest tenth of a year will it take if you start with $1,000 and you want to make that grow to $3,600 at 8% annual interest? And we're going to compound that on a quarterly basis. Okay, so here is our compound interest formula from our earlier work. The amount you wish to get in the future is $3,600. The amount you start with in the present, that's why it's called P, is 1,000. Interest rate as decimal, quarterly compounding, so m here, and the power is m times t. We have an exponential equation here because our variable is up there in the position of the exponents. So what are we going to do? Isolate the exponential and get this compressed as much as we can and simplified. So let's do this arithmetic right here, giving us 1.02. Next, we have to make sure the coefficient here is a 1, or else the logarithm process is much more complex. So we'll divide both sides by 1,000, and that gives us 3.6. Okay, now we've got this quite simplified. So now we'll apply the natural log to both sides. You could use the common log if you wanted. You could use log base pi if you wanted. But if you want to use the calculator to get a result, I would suggest natural log or common log. Take the log of both sides. Use the power property. Notice the whole power 4t comes in front. Now 4 and the log of 1.02 are just multipliers of your variable. So you can divide both sides of the equation by 4 natural log 1.02. And I encourage you to try this on the calculator and make sure that you're getting this on the screen. So the 16.2 represents approximately how many years it will take for that initial investment of $1,000 to grow to an accumulated value of $3,600. So that concludes section 4.4, PowerPoint slides.